Go in mathematics. The game of Go is one of the most popular games in the world. As a result of its elegant and simple rules, the game has long been an inspiration for mathematical research. Shen Kuo, an 11th century Chinese scholar, estimated in his dream pool essays that the number of possible board positions is around 10 In more recent years, research of the game by John H. Conway led to the invention of the surreal numbers and contributed to development of combinatorial game theory, with Go Infinitesimals being a specific example of its use in Go. Computational complexity. Generalized Go is played on n-times n boards, and the computational complexity of determining the winner in a given position of generalized Go depends crucially on the Koru rules. Go is almost in p-space, since in normal play, moves are not reversible, and it is only through capture that there is the possibility of the repeating patterns necessary for a harder complexity. Without Go, Go is p-space hard. This is proved by reducing true quantified Boolean formula, which is known to be p-space complete, to generalized geography, to planar generalized geography, to planar generalized geography with maximum degree 3, finally to Go positions. Go with Go is not known to be in p-space. Though actual games seem never to last longer than n2 moves, in general, it is not known if there were a polynomial bound on the length of Go games. If there were, Go would be p-space complete. As it currently stands, it might be p-space complete, exp-time complete, or even exp-space complete. Japanese Ko rule. Japanese Ko rules state that only the basic Ko, that is, a move that reverts the board to the situation one moved previously, is forbidden. Longer repetitive situations are allowed, thus potentially allowing a game to loop forever, such as the triple Ko, where there are 3 Kos at the same time, allowing a cycle of 12 moves. With Japanese Ko rules, Go is exp-time complete. Super Ko rule. This Super Ko rule, also called the positional Super Ko rule, states that a repetition of any board position that has previously occurred is forbidden. This is the Ko rule used in most Chinese and US rule sets. It is an open problem what the complexity class of Go is under Super Ko rule. Though Go with Japanese Ko rule is exp-time complete, both the lower and the upper bounds of Robson's exp-time completeness proof break when the Super Ko rule is added. It is known that it is at least p-space hard, since the proofing of the p-space hardness of Go does not rely on the Ko rule or lack of the Ko rule. It is also known that Go is in exp-space. Robson showed that if the Super Ko rule, that is, no previous position may ever be recreated, is added to certain 2-player games that are exp-time complete, then the new games would be exp-space complete. Intuitively, this is because an exponential amount of space is required even to determine the legal moves from a position, because the game history leading up to a position could be exponentially long. As a result, Super Ko variance moves that repeat a previous board position are not allowed if generalized chess and checkers are exp-space complete, since generalized chess and checkers are exp-time complete. However, this result does not apply to Go. Complexity of certain Go configurations. A Go endgame begins when the board is divided into areas that are isolated from all other local areas by living stones, such that each local area has a polynomial-sized canonical game tree. In the language of combinatorial game theory, it happens when a Go game decomposes into a sum of subgames with polynomial-sized canonical game trees. With that definition, Go endgames are p-space hard. This is proven by converting the quantified Boolean formula problem, which is p-space complete, into a sum of small with polynomial-sized canonical game trees Go subgames. Note that the paper does not prove the Go endgames are in p-space, so they might not be p-space complete. Determining which side wins the ladder capturing race is p-space complete, whether Japanese Ko rule or Super Ko rule is in place. This is proven by simulating QBF, known to be p-space complete, with ladders that bounce around the board like light beams. Legal positions. Since each location on the board can be either empty, black, or white, there are a total of 3 and 2 possible board positions on a square board with length n, however not all of them are legal. Tromp and Farnaby derived a recursive formula for legal positions Lm, n of a rectangle board with length meters and n. The exact number of L19 was obtained in 2016. They also find an asymptotic formula L approximately Bm plus n Cmn, where approximately 0.8 quadrillion, 506,399,258,457,145 b approximately 0.96 quadrillion, 553,535,933,837,387 and c approximately 2.975 quintillion, 734 quadrillion, 192 trillion, 43,357,249,381. It has been estimated that the observable universe contains around 10 atoms, far fewer than the number of possible legal positions of regular board size m equals n equals 19. As the board gets larger, the percentage of the positions that are legal decreases. Board size n times n3 and 2% legal L legal positions 1 times 1 3 33.33% 1 2 times 280 170.37% 57 3 times 3 19,683 64.40% 12,675 4 times 4 43,046,000 720 156.49% 24,318,165 5 times 5 847 billion 288,609,443 48.90% 414 billion 295,148,741 9 times 9 4.43 billion, 426,488,243 times 10 3 23.44% 1.3 billion, 990,148,792 1 times 10 3 13 times 13 4.30 billion, 23,359,390 times 10 8.66% 3.72 billion, 497,923,077 times 10 19 times 19 1.74 billion, 89,650,659 times 10 to 1.20% 2.8 billion, 168,199,382 times 10. Game tree complexity. The computer scientist Victor Alice notes that typical games between experts last about 150 moves, with an average of about 250 choices per move, suggesting a game tree complexity of 10-3. For the number of theoretically possible games, including games impossible to play in practice, Tromp and Farnaby give lower and upper bounds of 10-10 and 10-10 respectively. The lower bound was improved to a googolplex by Wari and Tromp. The most commonly quoted number for the number of possible games, 10, is derived from a simple permutation of 361 moves or. Another common derivation is to assume north intersections an L longest game for north turtle games. For example, 400 moves, as seen in some professional games, would be 1 out of 361 or 1 times 10 to 3 possible games. The total number of possible games is a function both of the size of the board and the number of moves played. While most games last less than 400 or even 200 moves, many more are possible. The total number of possible games can be estimated from the board size in a number of ways, some more rigorous than others. The simplest, a permutation of the board size in L, fails to include illegal captures than positions. Taking north as the board size 19 times 19 equal 361 and L as the longest game, null forms an upper limit. A more accurate limit is presented in the Tromp/Farnaby paper. 10 is thus an overestimate of the number of possible games that can be played in 200 moves and an underestimate of the number of games that can be played in 361 moves. Since there are about 31 million seconds in a year, it would take about years, playing 16 hours a day at 1 move per second, to play 47 million moves.